This is the brief on coordinate shifts and the crucial orthogonality condition. So what are we talking about here? We're diving into the math that ensures when we shift our viewpoint in space, things don't get all warped. It's all about perfectly preserving shape and distance, and it really shows this fundamental link between algebra and geometry. We've got 3 key takeaways on how this works. Okay, first up, what's an affine transformation? Well, think of it as a combo move. You've got a rotation, handled by a matrix, and then a simple shift, or a translation, which is just a vector. It's the standard playbook for how we mathematically describe moving an object around. Second, for this to represent real physical movement, with no weird stretching, we need a guarantee. Why? Because we have to keep distances the same. And to do that, we need what's called the orthogonality condition. This is kind of like the secret sauce. It forces the rotation matrix to keep everything rigid and stops space from getting skewed. And finally, using this special orthogonal matrix makes the whole transformation a rigid body motion. So think of it like this. You're rotating and sliding a solid block, not stretching some rubber band. This rigidity guarantees that all the object's properties, its shape, size, and internal distances are perfectly preserved, really cementing that link between the matrix algebra and physical reality. So that orthogonality requirement is the algebraic foundation that locks geometry perfectly into place during any coordinate change.